Welcome to Winsome Mathematics. Today we are going to learn one most important property of beta and gamma function. Okay. So this is the most important property again. So what we will do, we will see its proof and its importance and some examples based on it. So if you haven't watched the beforehand videos regarding this chapter, so must check the playlist and must watch it to be more confident in this chapter. Okay. So now we are going to see the proof without wasting any time. Okay. So before proof, we must know the importance of this relation. Okay. So now you were thinking, everyone will be thinking that what is this? How strange? Because we have come across this recurrence relation that was in the form of plus n plus 1 and this is in the form of 1 minus n. So something is similar but everything is different and everything is prominent by studying this property. So what is the prominence? So suppose whenever we come across this type of question 1 by 4 gamma 3 by 4 or simply gamma 3 by 4. Okay. So by using this relation we can solve this question, but using this relation we are getting stuck. Now you will think why is this so? So simple, just think that this is 1 plus n and this is less than 1, that is gamma 3 by 4, and 3 by 4 this term is less than 1, and but we can solve 3 by 2 by using this relation because this is greater than 1, that is 1 plus 1 by 2, and we used to write 1 by 2 gamma 1 by 2, that is 1 by 2 root pi. Very simple. But here what are we watching, observing that this is less than 1, so whatever we will write in the form of n must be in negative because 1 minus negative, 1 minus negative, that is something less than 1. So we can find this term by adding some terms in 1, positive terms in 1, we cannot find this term. Okay, that's why we are not using this relation. So must clear your confusion, must clear your confusion that why are we studying this and why are we not using this. Okay, so now everything is clear. So suppose try to convert 3 by 4 in this form. So whenever we will put n is equal to 1 by 4 here, so what will we get? That is gamma 1 by 4 and gamma 1 by 4 into gamma 1 minus 1 by 4, and 1 minus 1 by 4 is 3 by 4. So we are getting 3 by 4 inside this gamma function. Okay, now we can easily solve this. 1 by 4 gamma 3 by 4, that is equal to pi upon sine n pi. And what is the importance of sine n pi here? Because this is giving you angle of sine. This is giving you angle of sine, and this is fruitful term that is obtaining in RHS. Okay, so these were all importance of this relation gamma n into gamma 1 minus 1 is equal to pi upon sine n pi. So we will see its proof now. After the proof we will see the examples based on it. Okay, so let's see the proof of this relation. That is very simple. That what are we observing, that from somewhere we need to uh, obtain this term, that is gamma n into gamma 1 minus n. Okay, so we will take the use of relation between beta and gamma. We will take the help of this. Okay, so just by writing this relation, that you must remember, and you have remembered it. Okay, as I am thinking, because this is the most important that we have learned in previous video. Okay, so gamma m into gamma n upon gamma m plus n is equal to beta mn. This was the relation between beta and gamma. So now you were thinking that what is this, and we have to go here. So how will we go here? Okay, so first of all we will use the definition of beta mn. Simply we will use the definition, that is 0 to infinity x to the power n minus 1 or m minus 1 whatever upon 1 plus x to the power m plus n, and this is dx. Okay, so we can easily write that gamma m into gamma n upon gamma m plus n is equal to 0 to infinity x to the power n minus 1 upon 1 plus x to the power m plus n dx. No any problem. Okay, so now what we will do, that we have to convert this term into this term anyhow. So what we will do, and the most important thing to remember is also that uh, here also m and n is greater than 0. Okay, and here n is greater than 0. Okay, so what we will do here, so we will put m is equal to, so simply think that this is gamma n, this is gamma 1 minus n, and this is m n. So we need to remove this n, we need to remove this n, and so as to obtain this term. Okay, so what we will do, we are observing that something is adding into n, and here we need to frame gamma 1 minus n, because and gamma n is also already present here. Okay, so 1 minus n and 1 minus n plus n. So this term is also fruitful, because this is converting into gamma 1, and gamma 1 we know that this is equal to 1. So simply by substituting m is equal to 1 minus n, and m is greater than 0. Okay, and n is also greater than 0. Okay, so no any problem here. So n must will be n is greater than 0 and less than 1, so n must lie inside 0 and 1, that we can write easily. N belongs to 0 1. Okay, so now m is equal to 1 minus n, so we will put here. So what we will get, that gamma 1 minus n gamma n, this will become 1, like gamma 1 minus n plus n, and n cancelled, so this is 1, and gamma 1 is equal to 1. Okay, so this is equal to 0 to infinity and x to the power n minus 1 upon 1 plus x to the power m plus n, simply m plus n, m plus n. So this is 1 also, and this is dx. Now you are thinking, you were thinking that what we have done, how can we directly put here in the integration, because this is power, this is the power of x, not x. The integration containing x as a variable, not m and n as a variable. So simply we can substitute m and n without any tension. Okay, because integration, the x is a variable inside the integration. So limit is about x, not about m and n. So must be clear. Okay, must not hold any confusion. Okay, so now 0 to infinity x to the power n minus 1 1 plus x, and now this is equal to pi upon sine n pi. This integration is equal to dx also, pi upon sine n pi. Now you will be asking that how can we write. So for this is beyond this scope of beta and gamma function. We need to use the complex analysis to prove this. Okay, by using the Cauchy's integral theorem, that is by observing that the pole and pole of this by using the contour property. Okay, so this is beyond this scope. So just simply learn that 0 to infinity x to the power n minus 1 upon 1 plus x is equal to pi upon sine n pi. So this was all about this proof. Everything was simple. We started with what, relation between beta and gamma, then we observed that relation between beta and gamma is containing m and n both. Okay, so we need to remove m, because we need to uh, prove gamma n into gamma 1 minus n. Okay, so simply we need to prove it, so we have to frame this relation in this form. Okay, so what we have done, we have substituted m is equal to 1 minus n, simple. And now this is the uh, this is the domain of n and m. Okay, so here m and n must be greater than 0 as per beta function, and here n is greater than 0 as per gamma function. Okay, so simply when m is equal to 1 minus n, so m is positive, so 1 minus, what will become positive, 1 minus less than, the terms less than 1. Okay, and n cannot be less than 0, because n can't be negative. Okay, so it must be positive, so it will lie inside 1 and 0. Okay, so this is simple. And now we arrived at this term, that is gamma 1 minus n into gamma m. Now this is equal to 0 to infinity x to the power n minus 1 1 plus x dx, simple. And another doubt you might arise in your mind, doubt that might arise in your mind, that is simple, that how we have directly substituted. Okay, so simple, this is the variable of integration, this is not, this is m plus n. Okay, so x is the variable, not m plus n, so we can easily substitute. Okay, so now we derived it. Okay, so this was all about this proof. So again I repeated, and if you are unable to understand, so please repeat the video by going behind. Okay, so now we will see some examples to clear this chapter. Okay, so now these are some examples related to this property, and you are observing that something appearing in minus. Okay, so we can also solve this by using this property. Okay, so this is the importance. Okay, I have already mentioned the importance. Okay, so now we will see just by using this property. Now think that we have to solve this gamma 1 by 4 and gamma 3 by 4. So this is multiplied. Okay, so now to frame these terms 1 by 4 gamma 3 by 4 by using gamma n into gamma 1 minus n. So what we will do, so we will simply put n is equal to, now think that what we will put here, n is equal to 1 by 4. Okay, so 1 by 4, when we will put n is equal to 1 by 4, so this will become, this is gamma 1 by 4. Okay, and this is 1 minus 1 by 4. So why we have put 1 by 4 merely? Because we need to obtain same term, that is n and n here. Okay, and we are easily obtaining it, that gamma 1 by 4 and gamma 1 minus 1 by 4, and this is equal to simple pi upon what, sine n pi. What is the value of n here? That is 1 by 4, and pi, that is pi by 4. So now you can easily tell that pi upon sine pi by 4, that is root 2 pi. Clear? Because pi upon 1 by root 2 sine pi by 4, that is root 2 pi. Now first question is very clear, and all are very simple. Now this is gamma minus 3 by 2, so you will be thinking that this is in minus. Nothing, simple, just to what we will put here. Think what we will put here, because this is less than 1, minus 3 by 2. Okay, so this is less than 1, so what we will put here, something greater than 1. Simple, so that this term will become negative. Okay, so what we will put, simply we will put here uh, 5 by 2, 1 minus 5 by 2. 1 minus 5 by 2 is what, minus gamma minus 3 by 2. Simple. Okay, so we will put here, we can easily put, this is 1 minus 5 by 2, and we are obtaining gamma minus 3 by 2. Now we will be thinking that how to solve this question. So now think with yourself. Okay, also think that you can also write this as 1 minus 7 by 2. Simple. And this is 1 minus 1 by 2. Clear? Very clear. Now what we will do, we can easily obtain here from here that gamma 1 minus n is equal to pi upon sine n pi upon gamma n. Okay, upon gamma n. Very simple. This is very clear. Okay, so 1 minus n, so n is what, n is what, 5 by 2. So we will easily write gamma 5 by 2 here, and we know that how to solve gamma 5 by 2 by using recurrence relation, that is 1 plus 3 by 2. By using recurrence relation, that is gamma n plus 1, and this is equal to n gamma. And so what we will be observing, that 1 minus 5 by 2. So here we will be observing that this terms in LHS as usual, and simple here, so pi upon sine 5 by 2 pi. So we will solve sine apart. Okay, and then we will solve this term apart. Simple. So what we have to do in the second example, so simple, we will write it as this. Very clear, pi upon sine 5 pi by 2, and this is gamma 5 by 2. And now you can easily solve it. This is equal to pi upon sine 5 pi by 2, that is 2 pi plus pi by 2, and this is gamma 5 by 2, so 3 by 2 gamma 3 by 2, and in the next step pi upon, by using recurrence relation, that is 1 plus 3 by 2, that is equal to 3 by 2 gamma 3 by 2. Very simple. Pi sine 2 pi, 2 pi is in here in this quadrant, 2 pi is here. Okay, so 2 pi plus that, it is falling in which quadrant? Sorry, 2 pi is here. 2 pi 0 pi, 2 pi, 3 pi, 4 pi, 5 pi. So that odd appears here, odd multiple here appears here, and this is even multiple. Okay. So this is 2 pi plus, that is in this quadrant. So everything is positive. So simply sin pi by 2, that is 1, and 1 into 3 by 2 into 1 by 2 gamma 1 by 2. Very clear. And this two will go in the numerator. So this will become 4 upon 3, and this is root pi. 4 by 3 root 5. So this is the value of uh, gamma minus 3 by 2. So this is little bit technical. Okay, so tedious. So just don't frighten. We have concepts, so we can easily solve it. Okay. So now gamma minus 5 by 2, you can easily do it. That 1 minus 7 by 2. What you will do here? Simply you will convert this gamma 1 minus 7 by 2, that is equal to uh, pi upon sine what 2 pi here, 7 by 2 is 3 pi plus pi by 2. Clear. And this is into gamma n. What is gamma n? Gamma 7 by 2, because we can easily write 1 minus 7 by 2, and we can easily use this reason that gamma 1 will come into denominator in RHS. Okay, so gamma n, so n pi, what was n? N was 7 by 2, so we can easily write 7 by 2 as 3 pi plus pi by 2, and this is gamma n. Okay, so now what we will do? We will easily solve it by using recurrence relation, that is gamma n plus 1 and is equal to n gamma n. So now you are in habit of solving this gamma function easily, because we have solved in previous video. So what we will do here, we will simply use the technique that pi upon sine 3 pi plus pi by 2, and this is here 3 pi. Okay, pi 2, no, sorry, 0 pi 2 pi 3 pi. So this is odd, so 3 pi plus something falling here. Okay, so this here sign is negative. Okay, here sign is positive, here sign is negative. Okay, here tan is positive, so this is minus sine pi by 2, and so this is equal to pi minus 1. Okay, and this is into gamma 7 by 2, so we can easily use the technique 5 by 2 gamma 5 by 2 into 3 by 2 gamma 3 by 2 into 1 by 2 gamma 1 by 2, that is root pi. So 2 that is 8 upon 15, and this is root pi. Okay, and this is minus. So simple. Now these both were important, and this is very simple. Okay, so just comment the answer of this, and I am transforming it into 1 minus 1 by 2. Simple. So this will be equal to pi upon, use this relation that gamma 1 minus n is equal to pi upon sine n pi into gamma n. Simple. Okay, gamma 1 minus n equal to, simple. So 1 minus here what? 1 by 2. Okay, 1 minus 1 by 2. So you will use this 1 by 2 here, and here you know the value of gamma 1 by 2. Must comment it and must solve it. Simple. Okay, so thank you for staying so long.